Hello everyone, and welcome back as we continue to explore Stokes' theorem. We're going to start this video with another example. Here we want to use Stokes' theorem to evaluate this flux integral of the curl of our vector field, which is 2zxy squared, over the surface of a paraboloid 4 minus x squared minus y squared that's above the xy plane with upward orientation. So if we take a look at the surface, there's our paraboloid. It intersects the xy plane. We're only looking at the part of the paraboloid above the xy plane and the intersection. So the boundary of this surface is a circle in the xy plane. And we have our normal vector there pointing upward. Now in the example we did in the last video, we computed both the line integral and the surface integral. For this example, I'm just going to compute the line integral. And we'll revisit the surface integral later in the video. So if I just want to compute the line integral, I need to know an equation for this curve, this boundary. I also need to know that I'm traversing this boundary in a counterclockwise direction so that this orientation of the curve agrees with the upward pointing normal to the surface. Okay? Now if I want to find the equation for this circle lies in the xy plane, so I know z has to equal 0. And this circle is on the paraboloid, so z has to equal 4 minus x squared minus y squared. So I just set them equal to each other, which I've done here. Solve this equation. I get x squared plus y squared equals 4. So this circle is centered at the origin of radius 2. If I want to parameterize this circle with a counterclockwise orientation, I can use 2 cosine t, 2 sine t for x and y, and z is going to be 0 because we're in the xy plane, so the third component is 0. Now if I want a clockwise orientation, I would let this be 2 sine, I would let this be 2 cosine. But 2 cosine for x, 2 sine for y gives me a counterclockwise orientation, which is what we want. And then t goes from 0 to 2 pi. I'm also going to need the derivative of this parameterization, which you see here, negative 2 sine t, 2 cosine t, 0, and I need to plug this parameterization into my vector field. My vector field was 2 times z, which is going to be 2 times 0, x, which is 2 cosine t, and y squared, which is 2 sine t squared, which is 4 sine squared. So there's my vector field on the curve. I have a parameterization, its derivative. I'm ready to set up my line integral. So Stokes' theorem says that instead of computing this surface integral of the curl, the flux of the curl rather, I can compute the line integral where the line is the boundary curve of my surface. So that's what I'm going to do. And to set up this line integral, I need bounds going from 0 to 2 pi. Those are my t bounds. The vector field on the circle dotted with the derivative of the parameterization. That's how we set up these line integrals of vector fields. And when I compute this dot product, only the middle term is going to be non-zero because I have a 0 in the first component for this vector, a 0 in the third component for this vector. So I'm going to get 0 plus 4 cosine squared t plus 0. And now this cosine squared t, we're going to replace, as we've done many times before, with 1/2 plus 1/2 cosine 2t. When I distribute this 4, that becomes 2 plus 2 cosine 2t. And now I'm ready to integrate. So 2 integrates to 2t. 2 cosine 2t integrates to sine 2t, because remember I have to divide by that 2. And when I plug in my bounds, the sine both times goes to 0, so all I'm left with is 4 pi. Okay, and that's my answer. Just doing the line integral. So now I want to talk about something that's perhaps the most interesting consequence of Stokes' theorem, independence of surface. So let's consider this situation here, where I have this curve being traversed counterclockwise, and I have 3 different surfaces with the same boundary curve. So S1, I'm going to call this dome, S2 is going to be the larger dome, and S3 is just going to be the disk. That's the interior of this curve. So I have 3 surfaces, all with the same boundary curve, and all with upward orientation. So according to Stokes' theorem, I can set up these 3 relationships, where I have the line integral of some vector field over C equal to the curl of f dot n over the first surface, the second surface, or the third surface. But in this situation, C is the same for all 3 of these line integrals. So all 3 of these line integrals are exactly the same. So what does that tell me about the surface integrals? Well, if the boundary is the same, then these 3 surface integrals end up being the same as well. So the value of these three surface integrals is exactly the same. And this tells me that really, if I choose to compute the surface integral part of Stokes' theorem, I get to choose the surface I want to integrate over. So in this situation, if I was given a problem, it wouldn't matter if I computed the surface integral over this surface, or the disk. I would get the same value no matter what. So I could pick whichever one I want. So when you're using Stokes' theorem, and you want to compute the surface integral of the curl of f dot n on your surface, then you're free to choose the surface that you want as long as the surface has the same boundary as what you're given in the problem or the situation, and the surface satisfies the hypotheses of Stokes' theorem, that it's oriented and piecewise smooth. And it has to have the correct orientation to match the curve. As long as these things are satisfied, pick whichever surface you want that has the same boundary curve. Now this curve was particularly easy because it was just some kind of circle or ellipse in a plane. If you get more complicated boundaries, it might not be so clear what the best surface is to choose, so you might just have to use the surface you're given. But I'd like to revisit that example that we just finished, where our vector field was 2yxy squared, and the surface was the paraboloid 4 minus x squared minus y squared. We computed the line integral and got an answer of 4 pi. Now I'm going to compute the surface integral, but instead of computing the surface integral over this paraboloid, I'm going to compute it over a disk of radius 2. So just the interior of that circle that we had. So a disk of radius 2 that's in the xy plane. For this surface, our curl integral ends up looking like a Green's integral because the normal vector is just 0, 0, 1, or the vector k. So we just get that third component of curl. Okay, so now if we're integrating over this disk of radius 2, we're going to use polar coordinates, and we need to take these partial derivatives. Well, the partial derivative of the second component with respect to x is 1. The partial derivative of the first component with respect to y is 0. So we're just going to integrate 1 over this disk. So really we're just finding the area of this disk, and we don't need to integrate at all because we know the area of the disk is 4 pi. Well, let's go ahead and set up the integral using polar coordinates. So this curl integral is the integral from 0 to 2 pi and 0 to 2. Since I switched to polar coordinates, I need to multiply by r. And then I can separate this integral. The integral in theta is 2 pi. I integrate r to get 1/2 r squared. I plug in 2. That gives me half of 4, which is 2, times 2 pi gives me 4 pi. So there's a great advantage here in using Stokes' theorem. If you compute the curl integral, you can choose the surface you want to integrate over. Or if there isn't a good surface, let's say you have some strange curve where you don't know what the best surface is, you could still compute the line integral. You have the freedom. That's what Stokes' theorem tells you. So as we discussed when we talked about Green's theorem is a kind of fundamental theorem of calculus in 2 dimensions. Stokes' theorem is also a kind of fundamental theorem of calculus where it says if you integrate a type of derivative over a region, here it's a 3-dimensional surface, then it's really just an integral over the boundary, right? The fundamental theorem of calculus said that if you integrate over an interval, all you need are the values of the function at the endpoints, and that's the boundary of the interval. So this is one 3-dimensional version of the fundamental theorem of calculus. There is another 3-dimensional version of the fundamental theorem of calculus, which we'll talk about in the next section, called the divergence theorem.